So let's talk a little more about momentum. As we described earlier, momentum conceptually is a measurement of how hard it is to bring an object to a stop. More mass, more momentum, more velocity, more momentum. And so we say that the momentum is actually equal to, if I wanted to calculate it, the mass times the velocity. So to write that in equation form, obviously the right side would be mv, m times v, but we can't use m for momentum, so we use a p, and we'll see why in a minute. But if you want to calculate the momentum, use m times v, and that's how you actually calculate the momentum. So you can calculate momentum of individual particles. We've calculated in terms of carts so far, and in the last homework we did quarterbacks and melons and arrows and other things. But what we're going to see today is basically an idea about how, even if we know that the momentum doesn't change in the system, we can see how it goes from cart to cart. So let's use another one of these cart examples here. Okay, we'll do a real fast one. So what I'm going to have is we'll diagram it up real quick here. So I have a cart, and this cart has 2 bars on it. And it's moving, whatever, fast, and it's going to hit here and hit and stick to a cart that wasn't moving. And then afterward, they're moving together, so you have this cart here with the 2 bricks on it, and it has collided and stuck to, and now they're all moving together, this single cart. We're going to forget the energy for now. Let's just do the momentum bar chart. So let's put some colors on these and some speeds real fast. Make this one green. Now it's green over here. And I'll make the other one blue. So what's the situation? Well, this one is a 1/2 kilogram because it's just the cart. Still 1/2 kilogram over here. I know they're moving as one thing, but for instruction, we're going to still count them as individuals. This has got 2 bars on it, so it's 1.5 kilograms, and it's still 1.5 kilograms. And what we're going to say is it's moving to the right at 4 meters per second. And this one is stationary to start. And the question is, how fast are they moving over there? It's a fine question. So, this one is 1.5, this one is 0.5. If I draw their masses on here, this is 3 times this one, true? So if I make this 1, 2, 3, then this one can be 4. So it's 3 times as big. Same thing over here. Draw it the same way. 1, 2, 3. This one can be 4. And so we can see that their masses, one's 3 times as massive. The green one is moving to the right at 4 meters per second, so I'll make this 4 meters per second. And so we can talk about the total momentum. Well, it's 1.5 kilograms moving at 4 meters per second. 1.5 times 4, so the momentum is 6. Now, what are the units on that? If I were to calculate this, I'm calculating the mass, which is 1.5 times the velocity, which is 4, and so we end up with 6. But the units are silly because it's just kilograms for the mass times meters per second. So the unit for momentum is kilograms times meters per second. That's weird, but it is what it is. So, what's the deal here? It hits here, it picks up some extra mass, therefore it has to slow down. And if it slows down, what does that mean? That means that it's actually going to be going not quite as fast, right? Because as I go to draw this here, what I'm noticing is it's taller, which means it can't be as wide. So what is the new height here? Well, it's 1.5 times 0.5. That's 2 kilograms. I know that the total area has to be 6 because the areas have to match, which means the new speed is 3 meters per second. And I like this because the mass actually went from 1.5 up to 2. 1.5 up to 2. So we see we have an increase in the mass, so we have a decrease in the speed. It went up by 4/3, and then it goes, the mass went up by 4/3, and the speed goes down by 4/3, which is a weird thing. No, it goes up by, oh, it doesn't matter. Okay, good. Now, here's the thing that I find most interesting, okay? This is the diagram as we like it, but let's look over here a second, okay? Let's split this up into its pieces and see what happens. We see that the blue one is down here. We see the blue one is down here, and the green one is up here. And let's calculate the individual momentums of each of these. So we know they're moving at 3 meters per second. The green one is 1.5, and the blue one is 0.5. So 1.5 times 3 is, oops, wrong color, 4.5, and 0.5 times 3 is 1.5.
Let's take a couple minutes and see if we can't finish the last two questions from momentum number 2.
Sorry about that. When the video is done processing, it just starts playing, which is annoying. We see that the total momentum was 6 before and it's 6 after, but what's happening to the car? The green car slowed down. It was going 4, now it's going 3. So going from here to here, we're going to notice that the green car loses some momentum. That's okay, because the blue car had no momentum over here, and it goes from here to here, it gains some momentum. How much momentum did the blue car gain? We're going to use this notation. This triangle means change. The change in momentum of the blue car, it went from 0 to 1.5, was plus 1.5. What about the green car though? It had momentum of 6, now it has momentum of 4.5. What was the change in momentum of the green car? Negative 1.5. So we know the total here has to equal the total here, which means that the change in momentum for the green car and the change in momentum for the blue car have to be, interesting, they have to be equal and opposite. So whatever the green one lost, the blue one gained. And that's how the total amount can stay the same. Now, how did this actually happen? Well, during the collision, something interesting is happening. The green car is hitting the blue car. Is it applying a force? It totally is. So the question is, how does the force of the green on blue compare to the force of the blue on green? So this is the question, okay? This is the question on everybody's mind. And remember, the green car has 3 times the mass, and it's the one that's moving. It's going to slam into the blue one and make it move. Now, we know the blue one does exert some force back because it actually slows this one down. But what do we know? If we've been paying attention, we're going to notice that these forces are equal in strength, opposite in direction, and they act on the other object. We actually call this Newton's third law force pairs. Newton's third law force pairs are forces that are equal in strength, opposite in direction, act on the other object. Green on blue and blue on green. So regardless of the situation, anytime two objects interact, they always exert equal and opposite forces on each other. Okay? Never on the same object, always on each other. All right, so let's keep going with our momentum conversation here. So we know that this force happened, and that's important. And one thing that's kind of not inherent in there is the fact that as this collision happens, not only is the force the same, but the time that the collision happens is the same. So one of the things that we wonder is, how could you change the momentum of an object? Okay? How could you change the momentum of an object? Well, two things are true here. If you wanted to change the momentum of an object, you have to apply a force, and that force has to last for some time. So you have to apply a force, and that force has to last for some time. But let's see what happens here. If I were to plot the time and the force here, a cool thing happens. Because one thing I could say was like, oh, well, I'm going to apply a small amount of force, and that force isn't going to last for very much time. And it turns out that this area here would be the change momentum, and it's not very big. What if you applied a larger force, but it lasted for the same time? If I applied a larger force, but it lasted for the same time, we would see that, well, all of a sudden we have a much bigger area. And what if I applied in the original one the same amount of force, but it lasted for a longer time? This could also give you a larger change in momentum. So our idea is that if you wanted to change the momentum, you have to apply a force, and that force has to last for some time, where this little delta t here is how much time the force lasts. So it's the duration of the force. So what's interesting is that if this is our idea, if I come over here, didn't I change the momentum of my object previously? Well, each car doesn't change its mass, but if I change its momentum, I also end up with a change in velocity. So this is an expression here for the change momentum. This is also an expression for a change momentum. I wonder if those two expressions can somehow meet in the middle. Are they actually equal to each other? Let's do a little bit of algebra magic here and see if we can't make them come together. If you remember back to our original days when we were talking about the acceleration of an object, the first way we calculated the acceleration of an object is we knew that it was the change in velocity divided by the change in time. This is the slope of the velocity time graph. The next time we talked about acceleration, we talked about it in terms of acceleration is the unbalanced force divided by the mass. Does that ring a bell? Does that seem familiar? Well, if this is the acceleration and this is the acceleration, couldn't we set those equal to each other? So I'm going to get rid of the unbalanced part, but couldn't be this the force divided by the mass? Couldn't that be equal to the change in velocity divided by the time? And if we multiply both sides by delta t and multiply both sides by m, I end up with this expression that says the force times the time that the force is applied is equal to the mass of the object times the change in velocity of that object. And this expression basically synthesizes these two expressions into one. which I think is really interesting because it allows us to understand this a little better. Let's see if we can't take that and make it into some sort of everyday example for context. So here's the road, and you're driving down the road in your little car. You get your car out here, hold on. Okay, you're driving down the road, and up here you see a stop sign. Okay, you see a stop sign, and what are you going to do? Well, you're going to stop. But there's a couple ways to step on the brakes. You could wait really a long time and you could jam on the brakes, and that would be applying a large force, but then what's true about your stopping time? It's really small. Or you could apply a small force, but then your stopping time would be nice and long. Either way, what's interesting about this is your car has a certain mass and you need to change its velocity. But your two options are, you can apply a huge force and have a small stopping time, or you can apply a small force and have a long stopping time. I love the way this equation comes together because it helps us get a handle on this force-time relationship. If you want a smaller force, you need to increase the stopping time. And there's tons of examples of this in our everyday lives. Let me provide a couple of them. Get rid of these guys. Don't need this guy anymore. You ever seen on pole vault? Pole vault's a silly thing. I think it's fascinating, but still. I mean, you're jumping over a large pole. So here, I'll draw 3 dimensions here for us. So here's the pole, right? Here's the pole, and our pole vaulter has to somehow launch himself over this pole. But what's going to happen? After they launch over the pole, they're going to fall, and what do they fall onto? They fall onto this mat. Is this safer? I think it definitely is, because if they were just to hit the ground, that would be a huge force and a small stopping time. But if they're hitting the mat, what's happening is their stopping time increases, which means the force on them is so much less. What happens in your car? If you were to crash into something, if you're in your car and you're going 35 miles per hour, but you hit a wall, your car might come to a stop, but you're still going 35 miles per hour. What does the airbag do? Right? Well, the airbag deploys, so here's you, right? You're holding on to the steering wheel like a good driver, 10 and 2, right? You hit, the airbag deploys, what happens? So all of a sudden this airbag comes out of this here, so here was the steering wheel. You got this big airbag now, right? Better than hitting the dashboard or the windshield, right? If you were just to hit the dashboard or the windshield, you'd have a huge force and a small stopping time. But what the airbag does is it increases the stopping time, which decreases the stopping force. And that is a big, big deal.